Okay. So in embedded systems, in our case, because we are dealing with power electronics and motor drives, we use extensive simulation to develop the algorithm. Okay, and just like you saw the motor, the Pspice model of the motor, we use the same motor model, to see the flow of algorithm, how the algorithm is structured, right? Once we have the algorithm down, then we marry the algorithm with the microcontroller. Okay, so what becomes important here is, Pspice. We use Pspice. There are other tools such as Vissim. Has anybody heard of Vissim? Vissim, and I think this is something maybe you guys should have in your college, is you probably can Vissim, Vissim. Vissim integrates well with DSPs, PI DSPs. Okay.
DI doesn't give that.
No. This is a separate company called Vissim, and it expedites your algorithm development and your execution quite a bit. So, that is that same approach we are using, but we are using the same approach we're using Pspice, and then marrying it to our microcontroller, our hardware, right? So this approach we have to use because the people who code, software engineers, are not motor engineers. So we have to tell them, okay, this is how the algorithm flows, this is how the motor works. So we code it in pieces, and then we show them, okay, this is how it has to go, this is how the flow is, right? So in case of motor, we tell them first you have to look at the Hall sensors, right? And then how the Hall sensor signals are generated, and depending on what kind of control scheme we have to implement. So we tell them, okay, look at the Hall sensors, take the Hall sensors, and then come up with a firing scheme, right? So all of that, I'm saying it in a simplified way, but all of that goes into as a part of the strategy. So here,
Pspice can be linked to this algorithms.
Pspice can be used to develop the algorithms. Not the code, algorithms.
Okay, how to match the embedded?
I show you. So this is the steps we use. We develop high-level requirements. Now here, if we don't have a customer, then the high-level requirements are developed internally. Okay. So this here essentially is a high-level requirement document. Remember I talked about cell sheet, I talked about, yesterday I talked about how to create requirements. So this essentially has created requirements for us, right? So this document can be used to state requirements. Then you are going in and developing a flowchart. That is, now you are here translating customer requirements in feasible technical steps. So it's sort of a pseudocode, right? You have a pseudocode developed, and when you do Pspice simulation, you also have a pseudocode developed. Because Pspice simulation, how the signals are flowing, microcontroller is going to act the same way. Okay, so you have to use the whole Pspice model, the PI loop, the normalization, all of that is done inside the microcontroller. Right? So the same blocks we use for Pspice need to be inside a microcontroller for development. So, and then once you have done the pseudocode, now we have for a microcontroller 3 types of code. So one type of code is application code layer, okay, and then you have an application peripheral interface layer, and then you have a hardware layer. And I'm going to show you the 3 different layers we use for code development. Okay, so application code layer, application peripheral interface, and hardware. That is simply to modularize our code effort.
Indeed, it's difficult because depending on the priority of the certain software modules, you have to put in different interrupts also. And then
Right.
System.
Yeah, this is yeah.
So again, another division will come there. The software, like updating the PWM, interrupt kind of.
Yeah. Yes, I mean you have, if you're saying that the flowchart can become
Another division lies depending on the priority of the particular program, because some programs should be run immediately.
Yeah.
Some keyboard interface can be very slow. So we'll put in different interrupt levels.
Yeah. So you're saying that if you are in a one PWM cycle, right? In one PWM cycle, you have got various priority tasks, and then you can, if you continue to evolve or continue to add more requirements, you can even higher priority tasks, right? Let's say you have to respond to the keyboard. You're saying.
It's like keyboard will not come in interrupt. It will go on in infinite loop program.
Yeah.
Then PWM interrupt, whenever requirement comes to interrupt this program and do the PWM configuration.
That's the highest priority. That's the highest priority. Yes.
Then some exception comes, some fault. Then it comes in
different priority. So yes, so the execution gets interrupted.
Yeah.
That is correct.
And depending on the priority of the particular software models, you have to again distinguish them right in different segments.
Right.
Like instead of application code, like that again you have to.
I'll give you an example. I'll give you examples. What we place in application code layer. What we place in application. That the advantage we have here is we do not touch code layers in hardware layer and application peripheral interface layer. When we develop code, those codes in those categories is not touched. The only code we have to evolve is what is in the application code layer. That's the only one we have to evolve. Okay, so that becomes more modular.
Even peripheral interface layer and hardware layer you will not disturb.
Correct.
Everything must be completed only. Addition, subtraction must be application.
So you develop code such that
only the first one can be merged, right, rather than the other.
if you have a sufficient maturity level, right, so you don't have to touch API layer and hardware layer.
That must be
Standardized. Yeah. And then you modularize the pseudocode into the above three layers. Okay? And then develop code related to each of the modules. And then release and control the modules to the revision control. That basically are the steps we follow for code development.
But see, application code layer, it becomes complex depending upon the requirement.
Yes.
And the peripheral interface layer and the hardware layer, they must be able to meet to those specs.
Correct.
Sufficient amount of, otherwise, if the code layer changes, this cannot
That's what
be.
it said, maturity level, maturity level.
That is where your application code layer needs to refer to this API layer.
True, correct.
So that API layer and hardware layer is not supposed to change because of any changes in application code.
That's true, but suppose in some cases the code layer, the application layer doesn't match your requirements in this, then now we have to be.
You have not done your groundwork properly in that case, because hardware layer and API layer is supposed to be done. Because the hardware is
only
all the timing related issues are supposed to be handled in the application code layer. And hardware layer and API layer is supposed to be a dummy code which is supposed to execute the way it is written. It need not to be touched anytime.
So this basically is our flow chart. Okay. This is basically what we have. 1, 2, 3, 4, 5, 6. Basically the 6 steps we follow for developing code. And then we have, let's see here, before I go into here, this essentially is our 3 layers. Okay, so we have application layer, and then we have got application peripheral interface layer, and then you have hardware peripherals. So this is how you divide the code with different layers. Okay. This is the approach you use. And then there is a description. For example, I will not bore you too much, but for example, we have a file called mcu.h.
These details are provided.
These details, this embedded one is not in the book. We will be posting that on the website. All these slides are very new, so we'll be posting that.
I will have access to this.
Yes, you'll have access to all the demonstrations plus all the slides.
So efforts, so I should convert into products.
Yes, yes. So here, for example, when you define mcu.h, so we define data structures and the address mapping of all the peripherals. Now, if you look at mcu.h, where does it live? Okay, so it lives in the application peripheral interface layer. This is how we define various files, right? So you have got mcu.h, mcu-type.h, which is a common declarations file. Then you have the library configuration file, then you have peripheral file. So you have all these files which, and basically you do not touch the files here, you're basically developing your application code here. Okay? Here are some examples. I don't know how much. So we have a hardware diagram, then you have got the flow chart, then you match the files to application layer when you develop modules. Here how you match the modules
These
to...
all serial communication.
Yeah, this is just an example. This is just an
Will
example.
it not, serial communication doesn't do some delays?
You can have delays, yes.
No. Will have more delays than what is
Video generation, we call it application layer.
You have PWM peripherals, right? So you have PWM peripherals, you have PWM registers. So yes, you can activate it from the application layer, but you already have PWM modules, timing registers, right? So those can be activated by using files in peripheral layer as well as API layer. So all you're doing is passing the parameters, right? Saying, okay, set the timer register to this value, activate at this time. So you are calling on the peripherals and on the data structures through the API layer and the peripheral layer. But as we said, you're not trying to change those layers. Those layers you're trying to leave them as standards.
Okay, this is where is the PWM interface here?
No, this is just an example. This is not PWM example, but PWM example will be very similar to this I2C example. See, because this is I2C peripheral you have. Okay, so you look at here, we have I2C peripheral here. So similarly, you will have PWM peripheral.
But with this type of thinking, control bandwidth will become bigger. Because everything is going.
No, I2C is just an example.
Application layer directly deal with the
event logging.
hardware layer, no?
Yes.
In that case, in between not required.
It depends, right? I mean, you have application peripheral interface.
In this case, particular case, of course, serial programming.
So in this particular case, you are, you're not dealing with anything in application.
Peripheral interface layer.
Yeah, you're directly dealing with hardware layer. See, if you look at
Now, where is your feedback things are incorporated in the hardware layer?
Control.
Control feedback.
yeah, that,
Angular or the speed feedback.
yeah, you have peripherals there, right? You have analog peripherals. So hardware layer, you have, so when the data comes in, you are reading from the peripheral layer.
There are two things. Control software. interface
Right,
to
right.
the other machines or operators. That is on an application, you control also application, control the application.
No, control is an application. Control is an application. See, you're activating the peripherals through application API layer and the peripheral layer. Right? That's so the code, anything, it's like you're sending a message, right? It's like your brain sending a signal. Okay, see what's happening to your hand, right? What exactly is your hand feeling, right? So the same thing is happening. You're sending a message saying, okay, read the analog inputs, right? Read the I2C data, right? So you already have at the end of your hand program to feel what's in your hand. So the same thing is here. So you are trying to modularize your code so that when you are making your code, you don't have to worry about peripherals, configuration of the peripherals. You don't have to worry about activation of the peripherals, right? So that's why it becomes easier to do when you're developing complex code. The memory required for this kind of code is a little bit higher. If you do everything in assembly, of course, you'll have better code efficiency, optimization. But in this case, am I correct? In this case, you're going to have a little bit more overhead.
Definitely. When you go for high language,
Yeah.
you now get that trouble.
Right. Maybe another example we have here. All of these activities are activated through API and peripheral layers. And then you have different modules, and you place different modules in different layers. That essentially is quick and dirty of over embedded system development philosophy.